The final equilibrium problem is an inclined plane problem. In principle, it is exactly the same as the previous ones. In practice, we're going to have to learn how to train our brains to switch some axes around. So instead of redrawing the entire picture, I am going to go to a free body diagram. The free body diagram, we have to choose an object to isolate. It makes the most sense to isolate the block or the sled. So here's how I would do it for these. I don't draw them on a set of axes, it gets too hard. I kind of redraw the picture a little bit with only important information. So here's the hill, and that's at 19 degrees. And all I'm going to do now is draw the sled. Here it is, and the sled is 45 kilograms. The sled plus the kid in the sled. We're not going to change our approach. We are going to draw all the forces directly acting on the sled. Notice I don't care about the mass of the man. It serves no purpose. All I care about is there is a rope. The rope is parallel to the hill. It must act up the hill. Ropes don't push on things. Let's just call that F. Another force that directly acts on the sled is gravity. That acts straight down. Remember, the force of gravity is mg. The mass is 45 kilograms. So mg is 441 newtons. There is one other force we have to look at. We know the hill itself touches the sled. So there must be a force of the hill pushing on the sled, just like there is a force of the sled pushing on the hill. This is from Newton's third law. The force of the hill pushing on the sled acts in a very specific manner. See, there's an area of contact right here. The force that acts on the sled is always perpendicular to the area of contact. Now, yes, we know it pushes up, but I'm going to draw it like this to make it easier to see. It would act perpendicular to the hill. Also, if you notice, I have drawn all the forces so they would intersect in the center of the object, which is the model that is used. This force that acts perpendicular to the hill on the sled is something called the normal force. Not as opposed to abnormal, but in geometry, normal means perpendicular. So it's perpendicular to this area of contact. Later on, when we talk more about friction, we will revisit the normal force. We'll simply just call it N. If you notice, it's very similar to the other problems in the fact that we have three forces where one of them is known, one of them is known and the other ones are unknown. We need axes. We cannot use standard axes. In other words, we can't use these for X and Y. It would be too difficult to solve the problem. So how do we set them up? Normally, when we start looking at these problems, we have to decide what is the axis of motion. Now, if the object was sliding just up the hill, I would definitely call positive X up the hill. It's not moving, so it doesn't matter if it's up or down. If the object is moving, choose that as positive, the direction of motion. I am going to call positive X this way. One will always be parallel to the hill, or parallel to the incline, up or down, based on which way an object is moving. Since X is always parallel to the hill, rectangular coordinates say the other axis must be perpendicular to the hill. Always, always, always draw it in the direction of N. Those are our axes. Let me make sure that says Y. You really don't have much of a choice. Well, you do have a choice. If you want to make your life really, really, really difficult, you can choose these other axes. In a few days, I'll see that you might have finished it. Always, one parallel, one perpendicular. Since these are our axes, we now have to figure out how to resolve into components. We won't change our rules. I don't have to resolve F, it's along an axis. I don't have to resolve N, it's along an axis. I have to resolve mg. Remember what resolving vectors along axes mean. One has to be along the x and one has to be along the y. In this case, we draw the y first. This is one of the only times we resolve things to a y-axis. Here's one component, down. Here's the other component, down. These components will always point this way. One has to point down the hill, one has to point perpendicular to the hill. They both act down because look how you access or get to mg. The other thing we need now is the angle. This is the right angle. We are going to deal with this angle right here. If you look, you would realize this angle is 19 degrees, the same as the angle of the hill. You can figure it out by some right triangle work. This angle is 19. If this is a right triangle, this has to be 90 minus 90 here. Well, if this is a right angle, and that's 90 minus 19, that has to be 19. No matter how you look at it, the angle between the weight and the y component is always the angle of the incline. Now we have to use sines and cosines. This is where we remember adjacent and opposite, not x and y. Hypotenuse, included angle, adjacent side is cosine. So this is mg cos 19 degrees, which is 441 cosine 19. This component is mg sine 19 degrees, which is 441 sine 19. Be very, very careful when you are resolving into components. Now we can solve the problem. Sum of the forces in the x is 0. Sum of the forces in the y is 0. We're not changing our approach. Here's some x's. There's an x and there's an x. Here's a y and there's a y. So with our x equation, F minus 441 newtons sine 19 degrees equals 0. Our y equation, N minus 441 newtons cos 19 degrees equals 0. So you have to be very, very careful when you resolve into components. We can now solve for our two values. F is 144 newtons, let me draw the number correctly. N is 417 newtons. These are our two answers. This is the force the man must exert on the sled to hold it. This is the force the hill exerts on the sled. Quick question before we move on. If this problem stated the man was walking up the hill at a constant velocity, how would the answers change? And the answer is they would not change. If you are walking up the hill or down the hill at a constant velocity, this is true. 0 acceleration. The answers would not change. The answers would only change, in fact, only in the x direction, if the person was accelerating up the hill. We will revisit more of these incline problems later, but this should give you a good start to at least understand the principles behind resolving them into components.